So here we go. So we're going to talk about this integral that we did like so long ago. Now, because it's interesting, because I finally was able to solve it, and it took me getting smarter and better at this to finally. Oh, I forgot my video camera. Yay. Anyways, got a new haircut. Yeah. Anyways, yeah, I always get a new haircut in the beginning of the quarter when I'm about to leave. When I'm gonna leave, I want a short hair. So when I come back, I have long hair. Always the same policy. I don't want to cut hair in the middle of the quarter. Never do. I tried it a few times. Was horrible. So they always give me like a bad cut. I just rather have my mom cut it. Anyways, so over here we start with realizing that this is somehow the derivative of that. So interesting that if you get that relationship with these polynomials, when you get square root of tan, I think we discussed this. This is the square root of tan. Um, we do we do this. Oh, the opposite happened. Okay, so we want the same polynomial on top and bottom. That's what I started doing because I thought it would make it easier. It does some one reason or another, there's a pattern, and it makes sense because it's tan of x, so it's a human-made pattern, so therefore there's probably some kind of pattern to it. So yeah, it makes sense that the five would show up, in my opinion. So it makes sense. I got order of six, and then I already discussed why there's a no negative here. But in reality, it doesn't matter which way you do it. If you want to actually think about it, let's delete that. I like it negative. It shows more, um, because you pretty much cross this other side. Yeah, and then you get the order error. Order of error never defaults to anything other than six. Uh, and you find that the coefficient, there's no coefficient for x or x cubed because there's no coefficient in the this side and this side. And if you don't know, coefficient must match. It's a rule in math, really, because it doesn't make sense otherwise. If you try it, it just breaks out. Usually it breaks out. Sometimes it doesn't. I mean, there's certain cases where it doesn't quite work, but no, it always works. Pretty much always works. Yeah, it always works unless you're dealing with weird sine and cosine bullshit shenanigans. Then there's infinite polynomials. So even the I don't know. The Bessel function is weird too, honestly. But yeah, no, I was working on that a little bit and had to split it. It was quite weird how it doesn't work. I couldn't figure it out, but we'll see if someone else can figure it out for me. Anyways, after that you get this, and then you get this formula. You get n, you get coefficient match again, you get this in the end, and as you can see, you get this as a final something, and you put it out, put it out, put it out, put it out, reverse it, and you get this final formula over here, which is a long formula, but that. Oh, wait, that is big M. The mass, I was treating this like density, so I was treating this like a flap density. So that's the mass, I guess, in this entire equation. Uh, got it. Uh, Never doing that again. Yes. As you can see, I think there's actually a solution to this that's way easier. But let's go to Desmos. And let me type in this stuff. So I didn't test this out yet, actually. Funny enough, I know it works because I typed this in. It doesn't show any steps because it's a series, and for some reason, Wolfram Alpha doesn't like series that much. It doesn't show any steps to the opposite happen. Okay, good. Right. So let's just show this off. We start with the square root of 3, with the square root of 3 divided by 2, divided by 2. I love how showing this shows a little bit. It shows where each of the power and how much power is giving to the correction effect. When I add this in, it should have a correction effect to the whole thing. And it makes sense to go smaller and smaller of a correction if it's a finite error. Because you think about it, if it's smaller, going to a certain value, then it'll be a smaller correction to that value. That's how I see it. Uh, so. that, not sure if that's how everyone else sees it, but my eyes see it that way, which may be different in your eyes. Who knows? So it's like 15 divided by 2, more correction effect. Uh, Took forever for me to figure out how to get this polynomial, honestly. I wouldn't have figured it out without me waiting a year for me to get so annoyed of myself to actually do this shit. Literally annoyed myself to do it. Um, and with a little help of uh you know other sources. Uh yeah. I got way smarter than before, I guess. Or way smarter at figuring out strategies to get the help to solve this question. Uh, so it's 23 divided by 2, and then let's do a square root of tan x. And something's wrong. What is wrong with this integral? Should be right. Oh, this is the integral. Shit, I am stupid. Yeah. Yeah, this is probably right. Let me let me discuss this. So over here, it should be let me just do the integral of this real quick. So so it took me a year for me to get smart enough to actually figure this out, honestly. Um, okay. And not a year. It took me a few quarters. I don't know. So it's actually this is not a helpful analysis because at one, obviously, obviously that number is true. Um, or should be true. I don't know why it's not being true. Let's see something else. Maybe I am, huh, interesting. I think I did this wrong then. This function would be exactly the same. Should have been exactly the same as getting it from here. So let's see if I got something wrong. 48178 42462400159 over 800. Yes, I'm missing a polynomial. Okay, did I miss a polynomial over here? No, I just skipped over it because it's the same polynomial. It looks so similar. 1980. That's better, I guess. And that is 11 over 2. Okay, so now it should work. So at when it equals 1, so when x equals 1, right? It should equal 1 point. No, it doesn't. What is making this wrong? Well, probably is an ordered pair. So let me, hmm. Are you telling me that 10 of x, I'm getting this integral completely wrong and I'm messing up so badly that it's not working so well? 5, why is it 5 divided by, no, I'm getting it right. It's 3 divided by 2, 7 divided by 2, 11 divided by 2, 12 divided by 2, 19 over 2, and 23 over 2. 13367 1 5. Okay, so 1919 1 2 321 no 1980 8100 2462 400 17884 84 800. It should work, honestly. Everything says it should work. I don't know why. It just doesn't want to work today. Yeah, I don't know. Even this is saying the error should be minuscule from what I'm finding. Either my algebra and everything I did is wrong, or um, no, I really don't know what could have caused this error of my judgment. Is it, yeah, it's causing an error of order way bigger magnitude than it should be. Is it? Hmm. Yeah, I don't know. Huh. There's some kind of constant effect I'm not seeing. Maybe there is. Maybe I'm not seeing a constant effect. Because if I let me just do it too. No, 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 no. Let me s- see that that is the right integral, right? Right. Hmm. Mm. One. Oh, maybe it's because it's not registering correctly in here. Could be really due to just registration error. I don't see the error in here, so maybe it's a registration error. I don't know. It was. It was a registration error. Okay. So no, it wasn't. How? No, I'm. Hmm. Hmm. 2 represents form. All right, I'll figure it out one day. And then when I figure it out, I'll post. Oh, I'm a dumbass. I'm looking at the wrong equation. It's the red one. Sorry, stupid. So this one's what I'm trying to look at. Yeah, that makes sense. That's right. That's right. There is right. Okay, I'm a dumbass. Sorry. Yep. Okay. But we're good. We're good. It works. I was thinking, yeah, that doesn't. Right. And then with that said, we can find how much error there is compared to the actual function. So if you don't know, tan of x stops at pi divided by 2 basically. So we can figure out the error for pi divided by 2, which is 1.15, which is 1 point, that's a big ass error, I think. Let me try pi divided by 2. Yeah. There's an analytical solution to this, but I don't really know or how you got the analytical solution to this stuff. So it's 2.22 and it's 1.99. Uh, um, excuse me. What? Oh, yeah, because this Wolfram Alpha uses what's it called again? Uses numerical analysis. So this is a better error approximation to the Taylor series, obviously, when I go to the whatever error order it is. So this is the actual answer. So let's just get the actual answers and then let's subtract it with the um this real answer. 0.4. Uh, Uh, that's a big error actually. That's a huge error. You can figure that out. Well, 107 basically. Yeah. Interesting way you can solve it. I would not recommend this way. There's another way to solve it if you really want the real solution. So I'm pretty sure numerical analysis can get you wherever you want. But there's also this solution that you can look up whatever. How to no, not this one. Uh, the square root real quick. The opposite happened. Okay. All right, let's do that one. This solution, whatever. I'm not doing that because this makes no sense to me, even if I were to look at this for 5 hours. Doesn't make sense because you're going square root of u divided by u squared plus one. That doesn't make any sense for the life of me. And now it does make sense. I actually know how that works, but I'm not going to try to do it because it's completely a waste of time. Yeah, Wolfram Alpha is very powerful, but sometimes I feel like, well, this figuring out how to get this was way more powerful than figuring out how to get that because in reality, Taylor's theories is, in my opinion, more useful. Because numerical analysis is way more powerful in my opinion. Just plug into a computer, do a matrix, do a Ford or whatever, ODE 45, do a what are other ways to solve equations? And there's a few other ways. Um, Watercolor is one of them. Um, wow, far right. There's many ways. You can do Newton's or whatever. Uh, I would personally just use the ODE function in MATLAB and just finish it, whatever. Anyways, other things I did because this is a lot of what I did. Basically, finish this up and getting a solution that is half decent. Um, so I'm just gonna what uh, what's the actual function of this again? Okay. Uh uh Let me just put that in here. No, I'm not doing that. That'll be a pain in the ass. I think I'm gonna leave it off over here. I think it's solved at this point. I think that's the best solve I can probably give to that mass equation question I had like long time ago. What else do I have? I mean, I'm just gonna stop here. I have a lot of things I did. Honestly, I can show it off, but I need to start getting back into physics because this is where I should be, doing all these mass density questions, and this is where I should be. But I'm just going back and fixing up the previous stuff. Um, yeah. I finally finished hyperbolic a little bit more and finished up something else I forget. But yeah, I'm gonna probably stop here anyway, stop recording. Let me see.